All right, lesson 78. Can you see me? Am I on there?
A little.
All right, we got Joe videotaping it. Let's see how well he does. All right, example number 1. We're looking at excluded values. Now, excluded values are values that when we put them into M, it's undefined. So if you remember, we find those in the denominator. So what we're going to do, just like before, we're going to take 3m minus 12, and we're going to set that value equal to 0 to see where m is undefined. Okay? Joe, is it still blurry or we're clear?
Clear.
All right, we're clear. All right, good. So we solve this like a normal equation to figure out what the value would be. Add 12 to both sides. So we get 12 is equal to 3m. Divide by 3, so we get m is equal to 4. So if I put 4 back in to this equation, we see 4 minus 4. Okay, put the 4 in the denominator, we get 3 times 4, 12 minus 12. The problem with this is that you get 0 divided by 0. And you can't have 0 in the denominator. So that's what we called an excluded value. All right. Okay, in this it shows when we have excluded values, if we graph these, the function's undefined. And when the function is undefined, it's called an asymptote. Okay, an asymptote is a boundary line that the graph of the function approaches but never touches or crosses. You see here, we would have an excluded value at x equals 3. There's a dashed line there, meaning the graph would get real close to 3, but it'll never touch. And the same thing on this end. Okay, there's vertical asymptotes, and then there's horizontal asymptotes, where the function of the graph never will equal those values because they're undefined. All right, now, just like before, what we look at says determine the asymptotes. Well, asymptotes happen where the excluded values are. So when you have x minus 8, what value will make that 0? Well, x equals 8 will make that value 0 or undefined. That is the value of the asymptote, okay? And that's where we would have if we were to graph it. If we went over 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 is a vertical line like that, and that's where the asymptote of the graph would be, where it's undefined. Okay, now if I went back, let me go back a slide. Okay, you find your vertical asymptotes by whatever that value of, okay, whatever that value would be in the form x minus b that would go in there. Those are the vertical asymptotes. Whatever number's added to it gives us a horizontal asymptote. All right, so we'll look at this example to see if there's, so right here, this 3 is what would give us a horizontal asymptote. And we look what value make that 0, and that's x equals negative 10. So if we look at a graph here, this one, if we went all the way over to negative 10, okay, there would be a vertical asymptote, meaning the graph's going to get real close to it but not touch. Okay, and then at 3, we've got a horizontal asymptote, which goes this way. Okay, and the graph would go close to that horizontal asymptote but never touch. All right, here's what we call a parent graph. If we graph the value 1 over x, it looks like this. And if we see in the form, remember we looked at 1 over x minus b plus c. Okay, we look here, we would see that, well, what value of that would make it 0? It would just be 0. So we've got a vertical asymptote at x equals 0, as we see there right on the axis. We've got a horizontal asymptote where there's no number added to it. So the horizontal asymptote would be at y equals 0. So we've got an asymptote here, and the graph looks like this. Now it's called a parent graph, or a parent function, because the graph of it, all of the other ones in this form look like it, like a child. Okay, everything's going to look like this with the curve going that way and that way. And then all the other graphs are going to look like it, but just be a little bit different. All right, so let's take a look at this. Okay, remember this. If nothing else, what you need to remember is 1 over x looks like this. Okay, 1 over x. That's the parent graph. That's what the parent looks like. This is in this form since x is in the denominator, so it's going to look like that. Okay, we look horizontal asymptote, we look excluded value. What value will make that 0? X equals 4. That's our vertical asymptote. Then we go over here, this is the C, this is where you get your horizontal asymptote, and that would be y equals -2. So if I'm to graph this, we go over to x equals 4, 1, 2, 3, 4. There's a vertical asymptote here. Horizontal asymptote at -2, so we go down to, draw the line right there. All right, and then what we do, it's going to look like that one. So we're going to come down to here where these asymptotes sort of split it up into 4 sections. I'm going to go into this section, and it's going to look like the top of that is parent graph. We're going to go to this section. I'm going to graph it like that. And so it looks just like that one. It's just shifted down and to the right. All right, application soccer. Okay, soccer administration plans to have 64 regular players on a team. The players will be divided equally among the coaches. There will be 1 backup player placed on each team at the beginning of the season, in addition to the regular players. The number of players on each team Y is given by the following equation where X is the number of coaches. Determine the vertical and horizontal asymptote of the function. Again, vertical one, we look there, we'll make that 0, X equals 0. Okay, that is the vertical. Okay, we go, where is the horizontal asymptote? We look to this number. That would be y equals 1. So we got a vertical, we got a horizontal asymptotes, so we've answered part A. Then letter B, it says, if there are 4 coaches, how many players will each team have? All right, so once again, we look back here. Okay, X is the number of coaches. So all we do is we're going to put that number X, that number 4 into X. So we'd have 64 over 4 plus 1. We work that out. 64 divided by 4 would be 16 plus 1, 17. Okay, so if we had 4 coaches, we're going to have 17 players, and that's why.